So I hope you all had a good weekend. In the last lecture on Saturday, what I did was to sketch what is the S matrix, and just let's remind ourselves physically what it means. It's much more important to have a clear physical picture of it. So it represents the amplitude for a set of particles in the far past to evolve into a certain set of particles in the far future via interactions. Out of S, there will always be a part where the particles propagate freely from past to future, but that part is not interesting to us. So we call that 1 and we drop it, and we write S is equal to 1 plus IT. So we are really interested in T. Then, this has indices which you can write as P1, P2 for the incoming and K1. Up to Kn for the outgoing. So that's T. Then with a little bit of experience we noticed that T always contains a part which is 2 pi to the 4th delta 4 of 4 momenta. All of these actually, that's fine. And so this is something that we should drop. So whatever is left, we call it Im. So finally it's M that we are interested in calculating. So we are not interested in this factor and we are not interested in 1. Now at the end, the prescription for Im in scalar theory, pi-4 theory, which was the only case we considered last time, was the following. The very first diagram is this diagram. Now here, this is P1, P2, and these are K1 and K2. We can label the momenta as if these are incoming and these are outgoing. In that case, the delta function would have been P1 plus P2 minus K1 minus K2. But anyway, that's dropped. The structure of this theory is such that the correct delta function is always there. So we are guaranteed about that, so we drop it. Whenever we are sure about something, we can stop worrying about it. What else is there? Well, in a Feynman diagram, we were taught long ago, in the early lectures of this course, that each of these lines should have a Feynman propagator, I upon k squared minus m squared in momentum space. But the procedure for calculating this is different from the procedure earlier where we calculated Feynman diagrams for correlation functions. So, when you talk about Feynman diagrams, if somebody tells you calculate a Feynman diagram for me, the first thing you should ask that person is, do you want the Feynman diagram for a correlation function or for an S matrix element? Because there is a slight difference. If it was for a correlation function, then you would put a propagator I upon k squared minus m squared for each of these legs, and you would leave the momenta off shell. That is, you wouldn't require them, you would leave the momenta generic. You wouldn't impose any constraint on them. I'll explain in a second why. But if it's an S matrix element, you don't put any propagators, so no propagator for external legs. This is what we saw last time. Also, this quantity is strictly calculated only under the condition that P1 squared equals M1 squared, etc. In principle, these could be 4 particles with 4 different masses in a general theory. In this scalar theory, of course, it's a common mass, so all the P squareds and K squareds, they are all equal to M squared. Now, one question perhaps we didn't answer last time was, why on earth would we be interested at all in such an object with propagators for external legs and without using the on-shell condition? Why should we ever consider a 4-point function of scattering where the external particles don't satisfy P squared equals M squared? Is this a puzzle? Well, the answer to the puzzle is that correlation functions like that, off-shell correlation functions, can be building blocks for other Feynman diagrams. That is, if I have a very large Feynman diagram with 1 million interaction vertices in it, then each piece of that might be a 4-point function or some other function that I've already calculated. Now, if I take a correlation function and put it inside a Feynman diagram, I hope you realize by now that structure of Feynman diagrams is recursive. That is, for example, for 4-point function, if I calculate it to all possible loop orders, I could have a diagram like this with all kinds of loops and what order is this Feynman diagram? What order in lambda is this? 9. Somebody got 9 first. Okay. So it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 4-point vertices. Okay. Now it might be that in this structure, okay, I had already calculated this part. What does this part look like? It looks like a 2-loop correction to the propagator. Right? Now, will this line here be on shell or off shell? How many vote for on shell? How many vote for off shell? Okay. How many didn't vote? Yeah. It's off shell because only the 4 external lines in an S matrix element would be on shell. All the internal lines are not up to us. They arise from perturbation theory. In some sense, they are not really there. Okay? They are some kind of structure that arises by doing the perturbation expansion and giving it a physical interpretation. Okay? There's no choice because once I fix this to be some on-shell momentum and this and this and this, then all the others have to be as generic as allowed by momentum conservation at every vertex. That's forced upon us. That's the rule. So therefore, if this is not forced to be on-shell, it will be off-shell. Moreover, every internal line is generically off-shell because we've seen repeatedly that the Feynman propagator's I upon k squared minus m squared, an on-shell condition is k squared equals m squared. So the internal line would become infinity if we insisted that it's on-shell. And luckily we don't have to do that. Good. So this is an example to show you that even if I'm calculating an S matrix element in which all these lines are on shell, the internal lines being off shell means that I can use a previous calculation, for example, of a loop corrected propagator and just stick the result in here. I can just paste it in here. Okay, but that calculation I should have done keeping this and this line off shell. The calculation was done separately, imagine, just this thing. Okay. But since it was calculation of an ingredient to put inside an S matrix Feynman diagram, I would have wanted to keep these lines off shell so that I can insert it in somewhere inside the diagram. So do you see now that every little calculation you do can be inserted when I go into higher and higher orders. So Feynman diagram has this structure that within it are little sub-calculations, and I can patch all the sub-calculations together to get the full diagram. So this is the main motivation. There are also others for this conclusion, which is that correlation functions, they should be thought of as ingredients rather than physical quantities, and they are both off-shell and they have external propagators. In comparison, M matrix elements, which are S matrix elements after removing some trivial parts, these are on shell and they have no external propagators. And these can be thought of as building blocks while these can be thought of as physical observables, as we'll see in a few minutes. One side comment which I'm not going to get into detail, but it may be of importance to those of you who really will do gauge theory calculations. These in general are not gauge invariant in a gauge theory. That means these quantities will be gauge dependent in general. They will depend on my choice whether I chose Lorentz gauge or Coulomb gauge, but these have to be gauge invariant. Do you see that this is consistent with all that I have said? These are not required to be gauge invariant because they are not observables, they are building blocks. After we use them as building blocks, it's the job of the full Feynman diagram to be gauge invariant, not of the building blocks. But here on the right, we are talking about the full Feynman diagram for a physical process, and that has to be gauge invariant because the theory was gauge invariant to start with. So, of course, here we are talking of scalar theory, but if it was a gauge theory, then this would be gauge dependent, and this would be gauge invariant. Okay. Now this, of course, I wrote equals, but after I remove all this stuff now, let's write what it's equal to. What is this diagram now equal to with all the conditions I've put? No external legs, no delta functions. What is left? The coupling, very good. So this is equal to minus I lambda. This Feynman diagram means minus I lambda. I did it last time. Okay. So this is the lowest order term in M, and it's of order, first order in the coupling here. So what will be the corrections? What will they be like? Can you guess? So there will be more diagrams. So for example, there will be this diagram. In addition, there will be, this is scalar 5/4 theory. There will be this diagram, and there will be this diagram. These go by the name of S channel, T channel and U channel. That's a technical term that's sometimes used. We'll come back to it later. Anyway, there are these three diagrams. What order are they in lambda? Lambda squared, because lambda here and lambda here. So to calculate them, I'll put the vertex is minus I lambda. So I'll put minus I lambda and minus I lambda. Probably I'll divide by 4 factorial also. Then I'll do all the contractions. We have some combinatoric factor for that. What about momenta? So here I have, say, P1 and P2. What momenta will be here? So we did it some time back, but maybe you've forgotten. So I've just given some random labels for these two, but notice that this plus this plus this plus this is 0 by momentum conservation. So only one of these is random, that means arbitrary. So let's call it K like this. Then this one is P1 plus P2 minus K or whatever. I don't want to go into the science. The important thing though is that the calculation, so let's rub out these which are similar. The calculation for this thing is to say, okay, maybe we should write it. So this is such that when we add it to P1 plus P2, we get K. So this is K minus P1 minus P2. Sorry if it's too small to read. And these are all 4 momenta. And which of these are on shell and which are off shell? P1 and P2 are on shell. Good. So everyone has got it by now. K is off shell in general, and this is K minus P1 minus P2, which is also going to be off shell. Anything which is not manifestly off shell is not manifestly on shell is generally off shell. Okay, so the Feynman propagators for these two are I upon K squared minus M squared and I upon K minus P1 minus P2 squared minus M squared. Since K can be arbitrary, the rules require us to perform an integral d for K upon 2 pi to the 4th of this stuff. Okay, and that's pretty much the end of it. So this term in its contribution to the S matrix is 2 factors of lambda, some numbers which are combinatoric as well as all these 4 factorial and all that, and then that integral. It's over. What will this integral depend on after we do it? P1, P2 and M. Okay, so that's what we expect, because P1 plus, first of all, it depends only on P1 plus P2 actually, because of the structure of this diagram, and P1 plus P2 is the same as K1 plus K2, the outgoing momenta. So we don't expect any further dependence on anything. So whatever this is will be the answer for M. Now today what we want to do is to do an explicit calculation of something little more non-trivial but still at tree level, and loop level we are not going to do in this course. It's quite hard, but if I have little time at the end today, I'll give you some words about what loop level calculations, how loop level calculations are interpreted. We're going to do a calculation in quantum electrodynamics. This word is pretty misleading. Anything involving photons is electrodynamics, and anything in QFT is quantum after all. But quantum electrodynamics refers to the interacting theory of fermions with electrons, with photons. And the fermions could be electrons, muons, etc. So it's basically the theory of fermions interacting with photons. If you include scalars on this side, then it's a generalization. We've looked at that theory earlier, scalar electrodynamics. Okay, so here what's the theory? Well, we start with this. We notice that this has a phase invariance under psi going to e to the I alpha psi. We try to promote that to a local gauge invariance. We've done all this for the scalar case. So we introduce A mu such that this thing becomes and then of course in order to make A mu propagate, we have that. So that's the theory. And as I mentioned before, gauge invariance, trying to require it in this theory, converts it to this theory, which has 2 new pieces of information. First, that photons should be there, okay, and second, that they must couple through this very specific vertex, psi bar, gamma mu, A mu, psi. That's the only interaction term in this. All the other terms are quadratic and therefore free propagation terms. So the interaction term is IE A mu. Thank you. Absolutely. Is E A mu psi bar gamma mu psi. Just like for scalar electrodynamics, it has the form of A mu coupling to a conserved current J mu. So psi bar gamma mu psi is actually the conserved current for phase transformations in this theory. And it's proportional to E, so in that sense it's analogous to lambda phi to the 4th, which is proportional to the coupling lambda. Okay, so that's, yes.
What is the significance of iota in the member coupling? What if I choose it to be del mu minus E A mu then?
What if I choose it to be del mu minus E A mu? Okay, well, there's a very specific reason why we did this, which is that if psi goes to e to the I alpha psi, this is the phase transformation, this should be already a global symmetry for this theory, which is true if we have e to the I alpha, because psi and psi bar. Is not true if we don't have I. If this is just, so it must be like this. So what does del mu pull down? It pulls down I del mu alpha when I make that change here. I have to compensate that by a shift of A by del mu alpha. Okay, I can scale away E, but I can't do anything to I because alpha is real and A is real. So I have to have the I, yes.
Our function is that first diagram.
Yes.
In that diagram we need not
there's no mu in this. I've changed my theory. Here I was talking about scalars. Now I'm talking of a new theory. Until the point when I drew this line, I was talking of scalar phi-4 theory with the Lagrangian half del mu phi minus half m squared phi squared minus lambda 4. You remember this theory? We discussed it in detail. Now I'm talking of the theory with this Lagrangian. It's a different theory. So therefore you can't ask a question about this theory and that theory or other way around. These are not Feynman diagrams for a theory with photons or with gauge fields or charges or nothing. We are going to do that now. Derive from that. So first of all we have the Fermion propagator. And it's denoted like this with an arrow. And it is I upon k slash minus m, which is shorthand for so we keep talking about this side, but we always mean this expression. This expression is quite unambiguous because the denominator is a number and the numerator is a matrix, gamma mu k mu plus m times identity. Okay, this is 1 over a matrix, which is a little bit more confusing, but it just means that. Okay. So this is the Fermion propagator. Now, one thing we have to remember is this theory has complex fermions. They are not Majorana. Okay, and for complex fields, there is an intrinsic arrow which tells you the direction of charge flow. Complex fields have a concept of charge, and the arrow tells you the direction of charge flow. But for your own interest, you might want to label the momentum in a direction different from that arrow, for example, in the other direction. So what our convention is as follows. If we just write this, it means charge flow is that way. So if we write this with a momentum k, then charge flow is like this and k is also like this. So if there's nothing special, then this line means that. If I want to do it the other way, then I'll write the line with an arrow on it and another arrow below and put the momentum here. So now charge flow is to the left and momentum flow is to the right. Remember that for a given diagram, the momentum can flow either way. In fact, there's no real meaning which way it's flowing because k in general is off shell, so all components of k are anything. That's not the point. The point is that labeling it this way makes the momentum conservation have k appear in it with one sign. Labeling it the other way means k will appear with the other sign. That's all. It just has to be consistent. Doesn't have any definite physical meaning. On the other hand, charge flow has a very definite physical meaning, even in a virtual Feynman diagram. So, in this diagram, charge flow is to the left and k is to the right. So we put two arrows only if we need them. If we don't put this arrow, then this arrow indicates everything. It's a convention. For the vector field, we need to choose a gauge. So for the calculation we are doing today, Lorentz gauge will be fine. And in that case, so this is the vector field propagator in Lorentz gauge. And it is minus I eta mu nu upon. So that's it. Now there's one extra thing to be noted, which is that when we write S matrix, when we do S matrix calculations, we will have external lines, and of course we amputate the propagator for the external line, but the external line means a particle which is prepared or detected with a definite polarization. These are particles with spin. So I have to put in that information, what polarization I prepare it with or what polarization I detect. So there are external polarization factors There's nothing very surprising about them except that we have to keep track of the signs. So for example, for a fermion, if we have this structure, what am I saying? If we have this structure, and this is so I should make a mark where I'm putting my external, so I don't know what, there's no convention, but maybe I'll put a cross here. So this is the end of the diagram. Here the line is going to go and connect to other things. And this is an end where I have so remember, time goes from right to left. So these are incoming particles. Okay. So this needs one convention. This needs another convention. These are the two different orientations. So this one refers to, and let's say an incoming electron. What would this refer to? Incoming positron. Good. And what would this refer to? Outgoing electron and outgoing positron. Very nice. So let's write it so that we don't forget it. Okay, now you remember that these polarizations were given by things which we call U and V, and U bar and V bar. So we need some kind of rule, and the rule turns out to be not completely intuitive. This is U S of P, where the momentum is P, and it's labeled along that. Now in the second one, the momentum is still P, but I want the momentum to flow this way by convention because it's an incoming line, so it's better to keep it consistent. Okay, so it's certainly an incoming positron, but this certainly will not have a U, it will have a V, right? Because V's are associated to positrons and U's are associated to electrons. We did this last time. But in fact, this is a V bar. And the way to remember it is that, yes. 1 minute, don't ask at the same time, please. Yes. Not really. I suppose, but as I said, we haven't specified anything about whether, what are the components of P. So if I write the arrow pointing to the left and put all the components to be negative numbers, I haven't told you what are the numbers for P, right? So in that sense, but okay, if you take the convention, I think what you're saying could be right. If I simply take the convention that the energy component of the external P is positive, okay, so P is E comma some space vector, and then you're right, that with that energy positive, the flow should be to the left. Yes?
What is the cross represent?
Sorry? Cross represents the external point. So, this is external point. To be very concrete, imagine this first line in a diagram where I have two incoming electrons and then, not very good. This is a diagram for electron-electron scattering. So I put the cross here when I write it there, just to show you that this is the part hanging in midair while the other end of that line is attached to the diagram. So this is the external point. This one is the external point on this side because it would refer to these lines. Okay, so these are the rules, and now for the lines going on the other side, for the electron, this must be the bar of this, and P, so the convention is that P is, we try to label along with the electron for external lines. Remember that for internal lines, we don't really care at all It's for external lines that we should keep some consistent direction of momentum flow. For internal lines, it's just a pure convention. So good. So this has U bar S of P, and that only leaves Vs of P, which better be the last one. So one thing we learn is that when writing Feynman rules, we should start from the point where these arrows end on the outside. Put the U bar, follow it back, then there'll be some gamma matrix factors and other stuff, and this line eventually will terminate in an incoming line. We'll see that it's part of the structure. Where it terminates, I'll be putting a U. So the structure will be U bar something 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 U. And the something 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 are gamma matrices. Yes. 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 The arrows are very bad. Thank you. This diagram doesn't exist for electrons and electrons. Thank you so much. So it's nice to notice that charge flow has to have some definite continuity across the vertex, because the vertex involves one photon and two fermions with the charge flow aligned like this. So that charge coming in is flowing out. If both arrows were in, then charge would flow into the vertex and sit there forever. This clearly can't happen. So you see that this is an incoming electron. This is a virtual particle, so we can call it whatever we like. We can say it's an electron flowing this way, or we can say it's a positron flowing that way. Okay? But in this thing, whether it's flowing forward or backward or anything is of no consequence. Now it's what? Here, it's a positron. So we can, now sometimes people use dangerous words like, so this electron flowing forward in time because positron flowing backward in time. Nothing of the sort. It's just the charge flow is connected like this. The positron is flowing like this. This guy is flowing like this. Everybody is flowing to the left. There could be another diagram in which the charge flow goes through like this. And these are photons. So you'll gain some practice in writing Feynman rules and evaluating diagrams.
X can be regarded as infinite. If the line is to the right of the X, then X is minus, time goes to minus infinity.
X can be regarded as the point minus infinity, that's correct, or plus infinity.
The other two diagrams, X is
Plus infinity, that's correct. That's correct. But of course, just to repeat the obvious, no propagator is to be written for these. Last figure. Thank you. Thank you. I forgot to write that. So this one is an outgoing line, so the momentum should again go to the left. So this is it. It's just how it comes out. If you look at these are all derived from whatever we did last time, but I haven't done it. Okay. Basically the reason is that, just give me a minute when I write the diagram which I am calculating, we'll try to see there. There's an electron-positron scattering. We'll see what would have gone wrong if there was no bar for the incoming positron. Okay? Okay, that leaves what? It leaves the external line factor for the gauge field. Okay? And this again has two possibilities. One is where the X is put here, and for this we put epsilon mu of P, epsilon mu S. S takes the values 1 and 2 if the momentum is in the 3 direction. Now in a given Feynman diagram, I surely can't have all the momenta in the 3 direction. I can rotate my whole experiment maybe so that one momentum is in the 3 direction, the Z direction. The others will do whatever they do. So you just imagine that epsilon is chosen so that it would have transverse, that is 1 and 2 components, if P was in the 3 direction, and then you Lorentz transform it back, or you rotate it back to the true direction. So it's always transverse to this P. And plane polarized, then the star doesn't matter. Is only one. It's this. I wrote it somewhere. E A mu. So E at this point is the number, and A mu, which is this, and psi bar psi, which I can put the arrows like this. Now just a vertex like this, it's an ingredient in perturbation theory, so it can appear in a Feynman diagram with 6 different interpretations. What are the 6 interpretations? As I've drawn it, what does it look like? It looks like a photon coming from minus infinity and splitting into an electron-positron pair. But if I drew it like this, it would be an electron-positron pair coming in from infinity and annihilating into a photon. If I drew it like this, it would be an electron coming in, going out after emitting a photon. If I drew it like this, it would be a positron coming in, propagating out after emitting a photon. If I drew it like this, what would it be? Yeah, electron absorbing a photon and propagating on, and finally positron absorbing a photon and propagating. Now the lovely thing is none of these 6 processes occurs in nature. Yes? Because in this diagram I've depicted the photon as coming in, everything comes in from the right in my representation. So I've depicted it as coming in from minus infinity, and here I've depicted the photon as going off to plus infinity. If you think of time coming from the right, then you have. Okay, so none of these 6 processes occurs in nature. For example, nobody has ever seen electron and positron annihilate into a single photon, with very good reason. Do you know the reason? Momentum conservation. Good. Okay, so that's not all. The same momentum, after all, momentum conservation is exactly the same no matter which way I write the diagram. All these 6 ways, the momentum conservation requirement is the same. Okay, up to some signs, but it's really the same. The important point is that for on-shell situations, these diagrams don't satisfy momentum conservation, which means these are not themselves processes. Okay, but this is the perturbation theory vertex. That means in any physical process, this vertex will be inserted in one or more places, and as long as one of these lines can be off-shell, then our problem goes away. It's only momentum conservation and all 3 lines being on-shell which is not allowed. Okay, so we can't consider any of these processes to calculate because we immediately get 0, but we can consider a slight generalization. And that's what I'm going to calculate for you now. Let's consider a case like this. It can be labeled in many different ways, but basically I'm going to think of it as an electron of momentum p and a positron of momentum p prime incoming. Okay? And what comes out here. Now, this is one vertex, this is a different vertex. Okay? The theory that I wrote has only one type of fermion, that is the electron. For momentum. Sorry, I shouldn't put a vector thing. Thank you. Okay. But they are on-shell for momenta, so if you want, really you can think of it as a 3-vector because the 4th component is determined. Now, I could have written my theory with multiple different particle species. For example, I could have had electrons and muons and quarks and tau leptons. What would the Lagrangian have been? It would have been that Dirac action with del mu replaced by del mu minus I A mu, this action. But E would have been EI and psi would have been psi I, where I runs over the species of the particle. So this could be electron, this could be muon, and etc. The mass term likewise would have the I, because the masses are different for all these particles. So this is really what we mean when we talk about quantum electrodynamics. It's the coupling of the photon to all the fermions in nature. So therefore, in this process, let's say that for simplicity I start with this being E minus and E plus. Here I can choose anything. I could choose E minus and E plus, or I could choose mu minus and mu plus, or anything and its own antiparticle. That much I am forced, that one of them has to be the antiparticle of the other, because you see that it's the same arrow propagating through. So I am going to look for the case where this is a mu minus and a mu plus, and we'll see in a second what's the reason. The momentum is here K, and here it is outgoing label K prime. So this is E plus E minus annihilation into mu plus mu minus. So first let's settle on this process and ask ourselves, clearly this is a diagram, clearly it's non-trivial, that is it's a contribution to the S matrix. Okay, it's not just the particles passing through, they couldn't pass through. In this case, notice that the one term is absent. Okay, in the S matrix. Not that we are interested in it, but it's not even there, because can there be a 1 in the S matrix for this process? Can electrons freely propagate and turn into muons? No. So, there's no 1 term. Okay, that's one thing. This is leading order. Are there other diagrams for the same process to the same order? Then we have to add them all up. Answer is, what are they? T channel. Very good. Let's try it. T channel. Now, here's my electron. Here's my positron. Okay, now what happens here? Muon. This is okay? Doesn't look okay. Yeah, electron simply doesn't have a vertex to go into the muon from this Lagrangian. I mean, you're using physical reason, which is true, that lepton number is conserved. But why is lepton number conserved? Because this is the Lagrangian. Okay, lepton number is also conserved experimentally, that's a fact. But look at this Lagrangian. It connects psi with psi. It doesn't connect psi I with psi j. That's called lepton number conservation. Okay? As simple as that. There is no vertex for an electron to propagate into a muon. So this is not there. So there is no T channel. All S channel. This is called S channel. There is no T channel. Now can you guess why I chose these to be mu minus mu plus instead of E minus E plus? There's no other channel. If I had chosen E minus E plus, then I would have had to draw the T channel diagram. Okay? So, let's write that. If E plus E minus went to E plus E minus, then S and T channels. Okay? What about if E minus went to E minus E minus? There would be T channel, but no S channel. You can see that because E minus means both arrows, charge arrows are inwards, so they can't meet here and annihilate. So no S channel. So there's T channel, and what else? U channel. So T and U. So here the T channel is, these are the incoming arrows. This goes this way. You see the arrows are quite well satisfied. And everything is electron. All these 4 are electrons. No positrons. But I could also have that the outgoing state is like this. Because remember, I must label the momenta. And the momenta are associated to the external line. So you see that in this diagram the momentum K prime and P prime arise on the same line. But in this diagram the momentum K and P prime arise on the same line. So it's a different contribution. So I have to add it. This is U channel. Okay? So you notice that depending on what you choose, you get one or more diagrams and you have to calculate them all. So I chose the cleverest one, E plus E minus goes to mu plus mu minus, because it has only one diagram, so it saves us trouble. So now we need to finally, I think we have postponed it enough, now we need to calculate this diagram. So right away I can write down for you M. Let me write the whole expression. Let me make some space for it. And then you will see why it's reasonable in the light of the rules. So M is equal to okay, so now I need to also specify the polarizations of all the external particles. So in addition to momentum, I should give a spin label. So I'll give the obvious one, P prime and S prime. This means an electron with S polarization where S is 1 or 2. S takes the values 1 or 2. And this with polarization S prime where S prime also takes the values 1 or 2. And here K with R, K prime with R prime. We'll start with this, but we'll see that we don't always need the full information. So let me now write this. So that's it. No delta functions need to be written. And let's see what's the interpretation of this long expression. It says the following. Let's start with the incoming. So we start always with the place where a charge arrow goes out of the diagram. Doesn't matter whether it's on the incoming or outside or outgoing side. We start with that just as a convenience to write down these expressions. So this one is an incoming positron, so it has a V bar of P prime and S prime. This is what I have written. I follow it till I reach here. Here I am at the vertex, so this vertex I'll just put minus IE gamma nu. This vertex I put minus IE gamma mu. And this propagator is minus I eta mu nu upon P plus P prime squared, because this momentum is P plus P prime in this direction. So the idea here is that the gauge field propagator involves a mu and nu, because the gauge field A mu is propagating into the gauge field A nu. Okay, but that same gauge field comes with a gamma, because what was the vertex? Psi bar gamma mu psi times A mu. So whatever gauge field comes here with index nu, the vertex must carry the same index gamma nu. Okay, so now I think you can read off everything written there. Starting from here to here, I get the first factor. Mu and nu should be interchanged. So this is mu, good. Of course, it doesn't make the tiniest difference, but okay, if you want it that way, yes, because that's how I've written it. Would it have made any difference if I had labeled this as gamma nu and this as gamma mu? No, because eta is symmetric. Okay. Anyway, good to be very careful what we are doing. So that's done, and this one starts here with the outgoing electron. So U bar, then minus IE gamma, and finally V. U bar, and finally V. So that's it. Now you can see that if I had a T-channel diagram, then the incoming electron would have become an outgoing electron, and then we would have had U bar for the outgoing electron, and tracing it back it would have contracted with U. So the U bar contracted with U is typical of T channel, while U bar contracted with V and V bar contracted with U is typical of S channel. It describes the charge flow. Seeing this, you can immediately guess that, oh, this means the charge flow is such that an electron and positron incoming are both connected. Huh? You can read off backwards from this to that diagram. Okay. Good. Okay. Now what do we want to do with this? So now finally we have to face the question, what is this? Okay, so first let's simplify it. Minus I minus I minus I is plus 1. No, it's plus I. Then there's there's E squared. There's P plus P prime squared. Now notice that this is just a number, so it doesn't care about the gamma matrix stuff. It's not inside any of those things. So it can come out. And the remaining things are V bar, S prime, P prime, gamma mu, U S of P times U bar R of K, gamma mu, V R prime. These are now contracted by the eta. So eta is gone. Eta was just used to lower this mu to a lower mu index. So it's done. Okay? So that's it. Okay. Now, the physical quantity we observe is the scattering cross section, and it requires a fair amount of work to relate this to mod of m squared. Of course, you expect that there must be a mod of m squared because this is an amplitude. In quantum mechanics, the observable things are squares, mod squared of amplitudes, which are probabilities. So, cross section is related to mod m squared, and please keep in mind that for m, if there were many diagrams like S and T channel, I have to first add them to get m and then take the mod square, not take each diagram separately, find its contribution to m and take its mod squared. Why? Amplitudes add, and when I do that, then I get cross terms. When I mod square, I get cross terms. For example, in the mod square, the S channel diagram can come multiplying complex conjugate of the T channel diagram. These kind of processes are called interference. We know this already in quantum mechanics. You add up many things and you take the square. Then the cross terms are new quantum mechanical effects coming because of the rule that you must add amplitudes and not just add probabilities. So that's very good, and that happens here, except it doesn't happen in our example because we've taken a one diagram example. Okay. So what's the relation? I suppose I have to get rid of this diagram now. What's the relation between m and scattering amplitude? So I'll write the relation. And for the derivation, I'll refer you to my notes, which I've already sent updated up to today to Raghunath, and he'll put it on the website right after this lecture. So the answer is, with the conventions I'm already using, these are factors for the incoming electron and positron. Then there's a relative velocity factor, V minus V prime, where V is P over, I guess I interchangeably call it omega P and EP. I suppose it doesn't do any harm. Sorry. Okay. Then there's a mod K. Now I'm slightly baffled what is mod K. I have a feeling this is something I'm trying to do in the center of mass frame. And 1 second, just a little confusion here in my notation. Yeah, K is the good. So I'll be doing this in the center of mass frame. So therefore, P plus P prime will be taken to be 0. The 3 momentum is equal and opposite, and by conservation, K and K prime will also add up to 0. What's the physics of this process? It looks like, now time flow is not, it's not time flow now, it's a spatial picture of the process. So this is P prime, which is minus P. They come along the Z axis. By convention, we can choose that. Okay, but then when they scatter into, so this is the positron and the electron, they scatter into a mu minus and mu plus, and this angle is up to the particle to decide. It chooses whatever angle it feels like coming out at, but back to back is not up to it to decide, has to be back to back because it's in center of mass frame. And this angle we call theta, it's between the outgoing beam direction and the Z axis. Okay. So given that, now I can continue with my formula. So now I have mod K, which is the same as mod K prime. And then 16 pi squared E center of mass. Of course, E center of mass is the same as omega P and omega, well, it's half probably. So we'll connect all these quantities later. They are all pretty much the same up to factors of 2. Okay, all this, and finally, of course, m squared. So all this is to say that the differential cross section with respect to per unit solid angle of the outgoing beam is these kinematic factors depending only on the momenta and energies of the beam times mod m squared, which comes from quantum field theory. So this stuff has nothing much to do with quantum field theory. It's just how you convert a matrix element or a amplitude into a scattering cross section. So it involves some physics about making beams with some spread and all that stuff. That's in the notes. Okay, but now you see for the first time that we have something that can be measured, and it is measured all the time, and it's related to an m which is calculated using quantum field theory. So for this m, you have to remember everything of the last 10 lectures. Okay, it involves calculating a correlation function of free fields in perturbation theory. Then, once you've done that, put everything external on shell, remove the propagators, remove the overall delta function, and whatever you get, add up all orders and add up all diagrams that you need to keep and take the mod squared. So this is what we are going to do now. One more thing to say is that supposing you were calculating this to higher than the lowest leading order, then even if there was only S channel, you still have to take the leading order plus all the higher quantum corrections and add them before squaring. Just, you should always keep that in mind, that always add before squaring. Okay. I shouldn't rub out m because we have to square it now. Okay. Okay. So m squared is e to the fourth upon p plus p prime to the fourth. By this I mean the 4 momentum squared and then the result squared again. Okay. Now, I'll write this. I guess it's exactly as written on the board. Yes. Oh no, I found. Yeah, good. V bar S prime. So this one. What I'll do is I'll take this one, write it as V bar S prime P prime gamma mu u S of P, and then I'll multiply it now by its own complex conjugate, because I'm trying to mod square this. This I've already squared. Now I'll take this times its own conjugate and then this times its own complex conjugate. Okay. Now it's a little exercise to show, this you can do in tutorials, that if you have something like V bar gamma mu u and you take its star, you get u bar gamma mu v. Just read it backwards and put bar. Dagger. What dagger? Where dagger? Here. What does dagger mean? Transpose. What are we transposing here? No. Make up your mind. This quantity, what can we transpose in this quantity? What is this quantity? Vector, scalar, spinor, matrix? It's just a number. This is a complex conjugate of that number. All the indices are contracted here. Now, when you take the star of a quantity which is made by multiplying lots of vectors and matrices and all, you can write it as U dagger, gamma dagger, V bar dagger, okay, which would waste a lot of your time, because as you know, gamma dagger has no simple relation to gamma. It's sometimes plus gamma and sometimes minus gamma. But you can also write it as U bar, gamma bar, V bar bar. That you have to show in your tutorial exercise. Once you show that, it's wonderful because U bar is here. What is gamma mu bar? It's just gamma, but it's just equal to gamma mu. That's why we constructed it that way. Gamma mu bar is gamma mu. And finally, V bar bar is V. So this is the exercise to show. Therefore, this gets multiplied with U bar S of P. What index should I put for gamma here? Lower mu, no. Think what you are doing. This whole expression, you are taking the mod square. So, this mu is already going to be contracted with that. So, here I better take a new index, which is going to be contracted. So, this, and then multiply it, the other bracket, with this whole thing squared. And here I get the other gamma, nu. Alright? This is it. If you think this is complicated, then you haven't seen any real calculations in QFT yet. This is as easy as it can possibly get. And it's a very good moment for us to invoke a nice physical idea, which is the following. You see, this is going to be tough to evaluate because for S equals 1 and 2 and for S prime equals 1 and 2, similarly for R equals 1 and 2 and R prime equals 1 and 2. So we have 2 to the 4 expressions to evaluate for all possible ways of choosing the polarizations. Okay. Luckily, if we think about how an experiment is done, we can simplify our lives a little bit. Supposing I do the experiment with unpolarized beams. Okay. So I send into the experiment unpolarized beams. What does it mean I should do here? Sum over S and R. No, let's not worry about the outgoing beams. There are two different things. One is incoming beam is polarized or not. Second, outgoing beam, the polarization is detected or not. These are the options. Okay. So for the incoming one, when it's unpolarized, people are saying sum over S and S prime. Just sum over half. I have to average over S and S prime because they could be either one. It's unpolarized, so in a given one, I don't know which one it is, so I take the average. So that means half sum over S equals 1 and 2 times half sum over S prime equals 1 and 2. Now, for the outgoing beams, I don't detect the polarization, suppose. So what should I do with R and R prime? Sum over with half or not? No, everybody is sure of this. Good. Then I don't need to explain it. This is an example of inclusive. I simply include everything. When I include, I just sum over all of them. So average over initial states, sum over final states. That's the slogan. So I have to do that. And now you see, things will simplify here quite a lot, because let's do the sum over S. What things in this whole thing depend on S? Only this and this. Huh? Now we derived an identity on Saturday which told us what is the sum over S, US of P, U bar S of P. Notice that there are free indices in this. This is A, this is B. I am not allowed to contract A and B because this is on the right. I shouldn't think of this as U bar U. This is UA, U bar B. Look how it occurs in this expression. This guy has its indices contracted with these to make a scalar. This one has its indices contracted with these. So this index and this index are not the same. Instead of that, I simply replace this by P slash plus M. And now, here's a barred spinner, then a matrix, 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 and a spinner. So it's just one more matrix. What type of matrix is it? Basically gamma matrix. Because P slash just means gamma matrix times P mu. So you see 1, 2, 3 gamma matrices if I pick this term. And if I pick the second term, then just 2 gamma matrices. So that's how it is. Using all the other identities. So for V, instead, this one is P slash minus M. So I should replace. Now, where does V bar come in? This V with an arbitrary index and this one with an arbitrary index together give me P slash minus M. Okay. But now how do the indices work out? Let's say this is A, B, B, C, C, D and D. Now this is V with D and V bar with A. I get a matrix P slash minus M with indices DA. Now at the end everything is only matrices. And how should I contract the indices? Yes, I can take this V, I can write this over here. After all, I wrote it there only to show me how the indices are contracted. If I write it here, then I get P slash minus, so I move this over here and then I replace these two by P slash minus M, DA. So DA, AB, BC, CD. So what kind of product of the matrix is it? It's a trace. At the end it's a trace. So that's it. So this trick of averaging and summing over polarizations reduces the entire calculation to traces, and what we actually get is, so E forth over that in front, then trace, and the trace is P slash prime minus M E gamma mu P slash plus M E gamma nu, and a separate trace for this other factor. Also please notice this is the incoming positron and the incoming electron. Okay, this one came from the dagger. So this is the basic one. That means this all concerns the incoming objects which are all electrons or positrons. So the mass here is ME. In the other factor, it comes from the outgoing states which are all muons. So the mass will be M mu. Other than that, it will be pretty much the same thing with the momenta K plus M mu. So K slash plus M mu, gamma mu. This mu and mu have nothing to do with each other. Please don't think this is an index, this is just a label for the muon. Yes. So there's a 1/4 factor, thank you. The 1/4 is from the averaging over the initial states, and there is no further factor for the final state. So this is the answer for m squared. So we are doing fine. This is m squared, and it's equal to that. So now I can rub out everything else and continue with this calculation. Is updated. So now, for example, today you will get all lectures 1 to 11. But even the part concerning lecture 1 or 3, if I found any errors, I would have corrected it. So you should always delete the previous version and download the current version from the website. You will find there will be a few mistakes of the previous lectures which are corrected there. Okay, good. So, and you will find this derivation. So now the next step is to evaluate the traces. This takes a longish time. Probably to do it here would take about 15 minutes, but it's easy in the sense, what does it do? It just, you have traces of 2 gamma matrices, 3 gamma matrices, or 4 gamma matrices. You need identities, and you just have to keep grinding at it. So I'll leave all that to your wise tutors, and I'll write down the answer for you. Once the traces are done, the answer has to be expressed in terms of Lorentz invariants made out entirely from momenta. So P dot K, P prime dot K prime. These are all 4 momentum contractions. P dot K prime, P prime dot K. These are 2 of the terms. Then there is P dot P prime, K dot K prime. So that's the answer. On dimensional grounds, like the line above it, it better be 4 powers of momentum inside the bracket, and outside we get 4 powers of momentum downstairs. So m is dimensionless, which is what we expect. The way, if you look how we defined m, it's dimensionless. Good? Okay. Now, a little bit of physical thinking should convince you that we can take the electron in this process to be approximately massless. So we can drop these. Now, this is a kind of approximation you might make or you might not make, but there's one reason, very compelling reason why you should drop it. Okay? And the reason is that we are doing lowest order in perturbation theory in E. So that means that there's some error in our calculation, which is all the higher order terms we have neglected. So you need to convince yourself whether keeping a small quantity like ME is of the same order as the error that you have already introduced by neglecting higher orders in perturbation theory. And turns out that this error is smaller than the error induced by neglecting next order in perturbation theory. So to be consistent, you actually should just give it up. Otherwise you will be fooled into thinking you have got some very accurate result. Okay? But the accuracy of this is limited by what's the next order perturbation theory. That's actually true. Thank you. That's actually true. And so in that sense, maybe it's just something I'm telling you, but you could do the calculation, of course, and check it for yourself. It would be nice to check. There might be a lesson in this that if we have things like electrons going to muons, and given that muon is a couple of 100 times heavier than an electron, so it seems reasonable that the electron mass is 0 in comparison with that. I cannot tell you what would happen if you did E plus E minus to E plus E minus, whether you should keep or not keep it. Of course, it also depends on the external momenta. You see, the key point here is that, in these expressions, you have, actually I haven't thought through the whole thing, so let me not make any more comments. Let's just take it. Let's think about it later. Okay, now this is as far as we can get without choosing a frame. We indicated in the picture that we want these particles to come in along the z-axis. So it's high time we use that fact. So P we'll take to be E00E with lower index. It doesn't matter actually. And therefore we must take P prime to be E00 minus E. This is the statement of center of mass. And we also learn that E center of mass is 2 capital E. We also learn that omega P that appeared in our formula and omega P prime are all equal to E. Pretty much everything in this expression finally will reduce in terms of E. Now, what about the outgoing? So I have K mu, and this also has to have the same energy E, because they are back to back, the K's, the mu1 and anti-mu1, and their total energy has to be twice the energy of each one, and the total energy has to be ECM. So this also has to be E, but it has a freedom to have a 3-vector momentum K in any direction it likes. K prime is, you see how simple the center of mass frame is for 2 to 2 scattering. It determines so many things just from kinematics. And finally, of course, we have taken here this because now P squared and P prime squared are basically 0. That's the statement that we are neglecting the electron mass. But K squared is E squared minus K vector squared, and this should be M mu squared. Likewise for K prime squared. Okay. So now let's start to evaluate all the inner products that we have in that formula. So now what is P dot K? So we have to evaluate P dot K prime, etc., etc. So they are all very simple. P dot K, let's write a list here. First of all, P dot P prime comes here. So that is E squared plus E squared. Remember, we have to dot it with an eta. So 2E squared. Okay. Then what is P plus P prime the whole squared? So P squared is 0, P prime squared is 0. The cross product is 2P dot P prime. So from this we see that it's 4E squared. Okay. Then P dot K prime. So P dot K is actually equal to P prime dot K prime, and they are both equal to E squared minus K minus EK cos theta. While P dot K prime is equal to P prime dot K, and this is E squared plus E K cos theta. This is all kinematics, and there's very little you need to do with it. So if you put all this stuff together, it's a 2 or 3 line exercise to see that this is now equal to, I'll just write down the final expression. So E to the 4th is in front. 1 plus M mu squared upon E squared. 4, no, yeah, good. Plus 1 minus M mu squared upon E squared cos squared theta. And so now everything is, so the matrix element is now fully evaluated in terms of the only possible things. This is the mass of the muon, we know, this is the scattering angle, and E is related to the center of mass energy by a factor of 2. So that's the end of the matrix element. Now I have to bring back the differential cross section. This had all those so it had 1 upon 2E, 1 upon 2E, then this, so this was 1 over 2 omega P, 1 over 2 omega P prime, This was 1 over V minus V prime, where V's are given by, this was V minus V prime mod. This was given by P upon E minus P upon E. The three momenta divided by the energy. But since the electron is being taken to be relativistic here, so this is 1 and this is also 1, so this factor is just 2. Okay. Then K mod K upon 16 pi squared E Cm. So let me write the factor here, K upon 16 pi squared E Cm. When I put it here, mod K is square root of 1 minus m mu squared upon E squared. So okay, so it is square root of E squared minus m mu squared, that's mod K, and the denominator is 16 pi squared E Cm. We'll replace everything in terms of ECM at some stage. So ECM is twice E, or better, E is ECM by 2. Okay? And now finally, all that, e to the fourth, 1 plus m mu squared over E squared Okay, here I've just given you an indication where this comes from, and that's just the amplitude. So we're done. Now it's a matter of simplifying everything. So just collect, so replace E as ECM by 2 everywhere. That's all we have to do, and collect the terms. E squared by 4 pi has a name, it's called alpha, the fine structure constant. That's for historical reasons. So it's the way that we parameterize the electron charge in dimensionless units, that is in units where h bar and c are 1, and in those units this is approximately equal to, very good, and so finally this expression is equal to these 4s are coming because we have put E center of mass now, which is twice of E. And that's the end of the calculation for the differential cross section. The total cross section is just the integral over this, of this, over the solid angle, and you get a fairly simple expression for the total one also. Again, it's a very trivial calculation done in the notes. It's really not rocket science to integrate 1 and cos squared theta. So at the end you get 4 pi alpha squared upon 3 ECM squared into plus 2 squared. that's the total cross section. Both the differential and total cross section should have some dimensions. What dimensions should a cross section have? Length squared, which is the same as 1 by energy squared. It comes from this. All the rest of this is dimensionless. Same over there. In fact, as pointed out in textbooks, now that we've got the answer, it's pretty obvious what it had to be, because the dimension is set by E center of mass. This is the only physical quantity for the incoming state. So the cross section should be of order 1 by E center of mass squared. Also, we are doing perturbation theory to lowest order, which means order E squared or alpha in the matrix element, so alpha squared in the cross section when we square M. So alpha squared and ECM squared were known. 4 pi by 3 required all this calculation, but of course also we have got these corrections which are by the ratio of the muon mass to the incoming center of mass energy. Now of course we can imagine ECM much greater than the muon mass, that's in our hands, in which case this quantity simplifies to just become alpha squared by 4, so then d sigma by d omega is alpha squared by 4 ECM squared 1 plus cos theta, and sigma so these are very good approximations for sufficiently high energy incoming cos squared theta, yes. Thank you. Okay. Now so that I'm done for the day, but let me just close with one comment. Of course, there's a lot of machinery, and probably there are more elementary methods which could give you answers like this directly. After all, we've seen these kind of answers even in textbooks of non-relativistic quantum mechanics. Sometimes we see these kind of answers even in classical mechanics. Okay? But what is really special about QFT is not so much just this answer, but the fact that now we can correct it to arbitrary precision in alpha by simply computing more and more loop diagrams. Okay? And the key point here is that I can measure this in an experiment to arbitrary precision. Arbitrary precision limited by the experiment, of course. And I can calculate it to high precision, again limited by how much computer power or manpower I have available to me, using loop diagrams. And I can compare at higher and higher orders of accuracy, and without exception, all calculations in quantum electrodynamics have agreed with experimental results to very high order. So the best comparison, I think, is somewhere around maybe 8th decimal place, or maybe I'm out of date and maybe it's more than that. So that's the amazing and special feature of quantum field theory, that you can just go on to higher and higher accuracy. Of course, one shouldn't overdo it. After all experimental results are sensitive to, who knows, all kind of things, the presence of, I don't know, the Earth's magnetic field, or the moon, or the sun, or the person doing the experiment in the next room. So experimenters have their own problem to get accuracy very high. To the extent that they can do it reliably, then the theorist can do the same thing and they can be compared.